Okay, great. So today what we're going to do, we're going to do a little bit of linear algebra review, which is going to be relevant to both groups. This is going to be some like really basic stuff that everyone should know about linear algebra. Then for quantum mechanics group, we're going to continue with some linear algebra first, and then we'll start talking about like postulates of quantum mechanics and defining what quantum mechanics might mean and how to do it. And then we'll maybe do some simple examples, so on and so forth. I keep going there. I'm a little bit unsure how the ending for actually both reading groups are going to be like, because like I'm taking auditing a course in quantum mechanics right now, and so like I'm getting more ideas of what to tell you. Okay, that's one thing. For classical mechanics, we're going to do linear algebra today, and the next week, I guess, is going to be review of multivariable calculus. It's actually really easy if you phrase it the right way, and then we'll either we'll maybe do a little bit of classical mechanics, then a little bit more like different like calculus, and like alternate, do something fun with it. Okay. But hopefully it's not that difficult. Okay, so today we're going to talk about linear algebra. So what is linear algebra? So raise your hand if you were in Math 240. Or drop. That's okay. Raise your hand if you've taken 223. Okay, so raise your hand if you did not raise your hand. Okay, good. So what is linear algebra? Yes, and the other thing is, for the weeks that I assign readings, like today I'm just going to talk at you, but then on a lot of other days I'll have like a class discussion where I'll ask you guys something, you'll try to explain it, fail miserably, and then I'll speak. Something like that. Okay. I want this to be more interactive. I want you to ask questions and answer things. Okay. What is linear algebra about? Sure. Yeah, sure. You're studying vector spaces, and what's more interesting, you're studying also how these vector spaces relate to each other, right? So that's what we're going to talk about now. So this means we need to understand two things. What's a vector space? And how do you relate two vector spaces to each other? Okay, perfect. What's a vector space? So a vector space, like everything, is a set with some structure. This is the usual way that you should think about this. So, in fact, instead of answering the question, what is a vector space, let's start with a simpler question and ask the question, what's a group? So let's first give a definition for a group. A group is a set G with an operation. With an operation dot from G cross G into G that satisfies that satisfies some properties, whatever they are. So first of all, do people know what it means when I write G cross G? People know what G cross G is? No? Okay. So no? So G, okay. I didn't know I'd need to do this. I thought the first year courses were better than this, but that's okay. Is this visible what I'm writing? Oh, okay, good. So we'll do the following definition. Okay, if you have us, so another side definition, if people don't know what this is. Definition is, so if you given a set A, given sets A and B, the Cartesian product denoted by A cross B is the set. So A cross B is the set of pairs of AB, of elements, where A is in A and B is in B. So when I write G cross G, or any set cross any set, I mean I'm making a new set, which is just a set of pairs of elements, with the first elements from the first set, the second elements from the second set. Yes? People have seen this, surely. Yes? Okay. That is very different. I'll talk about that in the quantum mechanics one. But the tensor product, you need also some like linear structure or something. Well, you don't necessarily need fully linear structure, but something close to it, because it has like extra conditions. Because essentially, tensor product is you take a Cartesian product and then you remove some stuff from it. So it's kind of a more interesting space in that sense. Okay, good. I will use this notation a lot. This is hopefully something people should know from like, I don't know, from way earlier. Also, sorry, I just realized my laptop is not getting charged. That'd be really bad. Okay, good. So a group is a set G with an operation. I denote this operation by dot. So this is just like I could write F for function. I just denote it by dot. Just notation. So what does this notation mean? Can someone tell me what this notation means? So an operation dot G cross G to G. What does this mean? You. Yes. Exactly. So a group is a set G that also has a function that takes in two inputs and outputs one output, right? It takes in two things, outputs one thing. Okay, what are the axioms for it? So one is that, I don't remember the axioms. So one is associativity, right? Associativity. Meaning that A times B times C, if you multiply B times C first, get an element here, and then multiply by A, this is in fact the same thing as A times B times C, right? And once again, this is something that you need to specify, because this is like, I take this pair, and then I take this pair of elements, versus I take this pair of elements and then this pair of elements, right? If I have a function, it like an arbitrary function that takes in two inputs, gives one output, it might not do this, right? So you need something nice like this. Okay, then the other thing is you want an identity. So there exists, this is the there exists symbol. Okay, there exists an E, which is an element in G, such that E times G is equal to G times E is equal to G for any G in the group. Right? So that's good. So you need an identity. And the other thing, the other fact for groups is that there exists, so for any, people are familiar with the symbol? Yes? For all? Yes, I need a thumbs up from everyone. No? Not familiar? You are? Okay. For any element in the group, there exists a G inverse also in the group, such that G inverse is equal to G inverse G is equal to E. Okay. So, okay, this is what a group is. A group is a set, and then you have some operation where you can combine two elements and get another one out. Yes?
Do you need to specify closure as well?
No. Because you can't, if it's I told you already, it's a function G cross G into G. So by definition, it can't go out of G, because I said this is a function into G. So it can't escape. Okay, closure for a subgroup, yes, but yes.
Is it? Okay, I know addition is just like it's just an operation.
Yes.
Isn't it sort of like as if you just had addition?
Yes. Exactly. Exactly. The only difference is addition is always abelian, in the sense that A plus B is always B plus A. This is not required for a group. Yes, a group is not commutative. Now, so this is what a group is, right? Then I give you another definition. And we will use all of this later, so you should probably remember this. Another definition is an abelian group. An abelian group G is a group such that for all for any two elements in the group, A times B is equal to B times A. So this is what addition usually is, right? Addition is usually, you have all these plus being abelian. But then not all groups are abelian. So this is like a special kind of group. Yes? And we'll talk about that kind of group right now. In fact, the vector space is a abelian group. Okay. The other thing is, see how I'm writing multiplication here, right? Once again, this is just a symbol. I could have used any symbol here, right? This is not necessarily like multiplication. This is a very arbitrary thing I'm defining. I have some set, and then I define some rule of how to put things together in there. Right? That's all it is. Okay. So now, now let's define what a field is. This is kind of not entirely relevant for what we're doing all of this, but it is like good to see how all of these things are structured, and plus maybe some of you may not remember. So a field is, okay, can someone tell me the definition, or at least how the definition should start? First, like 3 letters, or like 3 words. A field is a, beautiful. A field is a set, yes. Guess how many operations are on a field? 2, yes. A group had 1 operation. Now let's see if we had 2 operations. Okay, is a set with 2 operations. Okay, now I'm going to start getting out the color chalk, because I think here the color chalk would be helpful. Also, my laptop always is turning off, so I have no idea if it like stops recording or continues recording while it's turned off. So we'll find that out at the end. Okay, good. So let's take these colors, 4 colors. Okay, let's say associativity is purple. Is anyone colorblind? No? Okay. Because I know a bunch of individuals who are colorblind, and I found that out like late. Okay. Anyways, so a field is a set with 2 operations. Both of these are binary operations. So a addition operation, which so a field, let's call it field F. So it takes 2 elements of the field, spits out an element of the field, and then dot, and then takes whoops, not G, into the field. Okay. Now we need to write down the rules. How do all of these operations work? Well, in fact, both a field is a set with 2 operations, and it is a group under both of these operations. So this has both. This has to have, both of these have to have associativity. Both of these have to have, what is this, identity. We will denote the identity here with a 0 and here with a 1. Okay, I'll make a comment about that in a second. Both of these have to have inverses in the usual sense. Both of these operations have to have inverses. Well, multiplication is like almost. And then you also have to have, both of these are abelian. Oh, whoops, I used the wrong color chalk. Sorry. This is supposed to be, inverses are yellow. Okay, don't worry, this gets fun soon. I'm just giving definitions and abelian. Okay. So in a colloquial sense, what is a field? In a colloquial sense. Okay, I gave some whatever, but what is a field? Yes.
Like it's either the reals or the complex numbers.
No. That's like yes, but that's not colloquial enough for me.
Something has a lot of values.
No, that's not it. So it's something where it makes sense to add two numbers together and multiply two numbers together, right? It's something, it's some set, and it's a set where it makes sense to add two things together and it makes sense to multiply two things together. That's all it is. Now, a key thing. So the people who have seen fields, they're going to tell me right now, you were not done yet. That I'm still missing more conditions. How many people here have not seen like a definition of a field in this way? Oh, everyone has. Okay. Well, wasting everyone's time here. That's okay. I'm having fun, so it's fine. So why is this not enough? Well, because here I said, okay, I have a field and I have two different operations on it, right? And if I told you, and as you can see, the field is an abelian group under this, and it's an abelian group under the multiplication. Actually, this inverses thing is not entirely true. Inverses accept 0 under multiplication, but that's fine. We'll talk about that later. So, if I just had an object that just had two operations on it defined, right? And all of these operations had some properties. Why would this object be more special than just a group that has two possible group structures, right? Right now, with what I've written down, this guy is on its own and this guy is also on its own. They don't talk to each other. These two operations don't talk to each other in any way. Which is why we need to write down some compatibility rules of how this would be compatible with this to, make it more interesting. Otherwise, if I just had these axioms, right, this would just be a group with two different group structures, and I just study it as a group. And it wouldn't make sense for me to consider a plus or a dot operation because they're unrelated. I just study them separately, right? Why would I study both of them at once if both of them are completely unrelated? Which is why we're going to relate them. And so you have the kind of, what I like to call the kind of compatibility axioms of addition and multiplication. And I don't remember all of them. I'm going to be honest with you. So the conditions are something like, you have b times x plus y. It's like the usual things that we all know, bx plus by. Like it works how numbers should work. I don't know. What else? Oh, well, we have associativity. What else is there? Oh, yeah. You have something like a times b times x plus y, like this is equal to a times b times x plus y. There's something like this, and like there's maybe a few others, but essentially it works how you would expect it to work. Yes? Probably. Like I know there's like one or two more, and I just don't remember what it is. But like it works how you would expect numbers to work. Yes? Yes? Is that a satisfactory answer? There's a lot of things in here that I will like. Some things I'll prove really rigorously. Some things I'll be like, well, it's clear. Because the point isn't to prove things rigorously. The point is maybe to try and understand something. Those are surprisingly like unrelated things. No? Okay. Oh well, so you don't. So that's not allowed. Oh, what would happen? Well, so from all of these axioms, if I wrote them down, one of the things that you can show is that, so 0 is the identity of the plus, 1 is the identity of the multiplication, right? Because of using the compatibility axioms, you can show that 0 times anything is equal to 0, right? And also you have that 1 times anything has to equal to 1. And I think from all of this, has to equal to a, right? And so if 1 is equal to 0, you get that a has to always equal to 0 for all a, meaning that you have only a single element. And so I guess you want identity 1 to be not equal to 0. Otherwise, with these compatibility axioms, you get that it just has to be like a thing with one element, which is just 0, which is incredibly boring and useless, and I don't care about that. Okay, for our purposes, this will always be the real or complex numbers. So a field will always be real or complex numbers. I will not talk about final fields. I will not talk about any of that because I don't care. Things are either a real number or a complex number. Okay, it's good to understand that you can think of this as a set and it has two operations and it does stuff. Okay, good. So now let's finally go back and define what a vector space is. What is a vector space? It is a set with two operations. Actually, that's false. It's a vector. You always have a vector space over a field, so it's two sets and two operations. Okay, so V is a vector space. So usually V dot means vector because that's vector is a very long word. A vector space over a field F. So well, actually no. V a vector space over field F is a set. V, okay, with operations. So you have an operation plus V cross V to V, and you have an operation multiplication dot that takes in element of the field, takes in a vector, and outputs a vector. Okay, so I will write this as follows. So I'll write that V is an abelian group under addition. Yes.
So is a vector, a vector space, isn't it sort of a set containing a set, two sets and two operations?
A set containing two sets and two operations. No, it's the thing that we call the vector space is the set V, but then it has an associated operation from some other set in V into V. So it's like a vector space isn't, in some sense, it's not the set. It's like the combination of. Usually, how people would write this is something like they'd write like a vector space is V, comma. It's like the V dot. Well, no. V plus, and then dot like sub F or something like this. It's like a vector space is this whole triplet of both the set and the operations. It's like all things together. It's not, just a set. Okay, so V is an abelian group under addition. That's straightforward. And then there's some compatibility axioms again. You once again have some compatibility, which I don't remember. There's like 8 axioms for what a vector space is. That's so many. Who can remember all of them? So, like, the important one is like A times, so lambda times V plus U is equal to lambda V plus lambda U. And then maybe there's some more. But, okay, you can look that up on your own. Please open Axler and read the first, 4 pages. And it will have less than what I told you now. But it will have the right compatibility axioms. Okay. Important question. Do people understand why I'm calling this the compatibility axiom? Why am I calling it the compatibility axiom? Who talks to each other? Yes, how the two operations talk to each other. That's why I'm calling this compatibility axiom. So note that here, this is like I'm taking the pair V and U, and I'm taking the pair V and U, and what am I doing? Sorry, what was I saying? I'm taking the pair V and U, and I'm doing an operation here with a plus, and then here I'm taking a number from F and a vector from V and doing the multiplication. Right. This is where that one comes in. Right. Here associativity actually matters. So lambda times alpha V plus U. There we go. Here this matters. Lambda times alpha times V plus U. Okay, why does this matter? Because actually, this is the multiplication of elements in the field. Lambda and alpha are in the field. So this is the multiplication of the field. And this is the multiplication of a field times a vector. this dot is not the same as this dot. It's just that people are usually very lazy to. Let me actually, instead of dot, do like dot v. So dot sub v, so that you know this is the multiplication of a number by a vector, and then by dot f we'll do so. This is dot f. This is dot v dot v, and then this is dot f dot v. There we go. So it's like if I multiply the vector by lambda, by alpha, and then I multiply this new vector by lambda, that's the same thing as multiplying these two numbers together first, and then multiplying that by the vector. Right? You can see that this is I'm multiplying the vectors each time. Here I'm multiplying the numbers then the vector. They're different operations in a sense, which is why you need this compatibility axiom. Okay, yes.
This dot v, is that a binary operation?
I forget how a binary operation is defined.
I think it is.
A binary operation I thought a binary operation has to be from the same set. It has to be like v cross v. I don't remember. It's like that's just a definition. Like that's just how to name a thing. That's not what's important. This is not what this is about. Okay, but now we know what a vector space is. Okay, let's try and quickly characterize a vector space. For that, people can survive without the colorful stuff. Yes? Everyone got that down? Okay. So now, let's talk about something new and, well, no. The same thing you've all seen before. I will introduce, what will I introduce first? I'll introduce first the span of something. Okay. So, definition. Actually, yes, okay, definition. Let's change colors once in a while. I think that would be fun. So definition. Given finitely many vectors, so given finitely many vectors, when I say vectors, I immediately imply that there's some vector space and these vectors are contained in that vector space. So v1, vn in v. Let's do vk. V sub k and v, so there's k vectors, yes? We define the span to be. So v is a vector space. Define the span to be span of v1, vn, comma, or vk, comma. This is the set of all possible linear combinations. So I take a1 v1 plus dot 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 ak vk. So ai is in the field, and these v's are these vectors that I chose. Yes. So if I have some vectors, what I can do is I can take them and I can add them, right? But in my vector space, I have more stuff. I can also multiply stuff by numbers, right? So why not? I just take each vector, multiply it by some random number, and look at all the vectors I can make up from that. Yes, that makes sense. Can someone tell me why this is something that is interesting? Why is this interesting? Why are we looking at this? Why is it useful that given some vectors we construct something like this? What does this tell us for these vectors? What is this? If I give you k vectors, what is the span of these k vectors? Like, exactly. That's the whole point. If I give you some vector, so I guess I didn't define what a subspace is, but it's intuitive, right? If you have a vector space, you can have a smaller vector space inside of it, right? Which has all those rules, but it's like embedded into the initial vector space. Okay, subspace is the usual thing that is subspaces. Okay, so the span of some vectors is the smallest possible subspace that would contain all of these vectors. So this is the key idea. So span of vectors, some vectors, is the smallest possible subspace containing these vectors. Let's think about that for a second. Right? Why is that the case? Right? Because suppose I have, let's say I have two vectors, not k of them, but just two vectors, right? If they live in some subspace, that means I should be able to add these two vectors, and that would be something that still makes sense and be in the subspace. Oh, this was completely not recorded. That's okay. Something that would stay in the subspace and still make sense. Suppose that I had it should also sorry, let me restate. Suppose I have two vectors. If I want to look at and those two vectors are in a subspace, then I should be able to take those two vectors, add them, and that should still stay in the subspace, right? But also I should be able to take a vector and then scale it by some number, and that should still be in the subspace, right? And so in that case, what you're doing is, okay, if I can construct other vectors in my subspace by taking some vectors and then adding them together and multiplying them by some numbers, how about I just look at all the vectors that I can construct by adding things together and multiplying stuff by numbers, right? And turns out that just gives you back the smallest vector space that contains all of these vectors. Yes? Right? If a vector space contains these vectors, then it has to contain their sum and their multiplication of them by some number, right? And so in the you just kind of do the most intuitive thing, and you build using these vectors, you can build a new vector space this way. Yes, makes sense? Do people now see why the span of some vectors is the smallest possible? So I didn't explain what first of all, I didn't define what it means to be the smallest possible subspace. But the smallest possible subspace kind of is intuitive in the sense that there isn't something that contains less vectors, whatever less might mean. So I said I didn't define it and then give you an answer without defining it still. Okay, but you know, you can think of it as like, suppose I remove the single vector out of this, right? What would go wrong? Well, obviously the vector that is that linear combination wouldn't be there, and okay, that fails. So smallest in that sense. And it's a subspace in the sense that if you take any two things from here, you add them, you still stay in here. And then if you take some number, you multiply anything from here by some number, it's still in the vector space. So in this case, what is a vector space colloquially speaking? It's a set where you can do what? Yes. So always think of a vector space, maybe not always, maybe I'm wrong. Think of I always think of a vector space as not these axioms, because that's too long and too complicated. It's something where I can add stuff together and I can multiply it by a number. That's it. That's all there is to it. Everything else is just like, oh, trying to make it like the thing that you would expect it to be. Everyone knows how to add stuff together, right? Everyone knows how to multiply by a number. Right? You don't need all this. Well, you need it, but it's like you need to understand what this is really saying, right? You don't want to get lost in the details. Okay. So we took some vectors and we made sure that you can add them and that you can multiply them by a number and created a subspace this way. Okay, good. Now we introduce the concept of linear independence. Very important concept. Okay, we're still on track. So linear independence. So I'll just give the general definition and then we'll talk about it later. So well, like there's like a slicker way. I'm trying to see if there's a slick way to like phrase it. So linear independence or maybe linear dependence. So I'll just define linear independence. So vectors v1 up to like vk are linearly independent if, let's see, if vi is not in the span of v1 up to vi minus 1, vi plus 1, vk, for any I from 1 to k. So what is this saying? What is this saying? This is saying that, suppose I have k vectors, v1 up to vk. This is saying that if I took one of them, I cannot express it as a linear combination of the other ones. Do you agree? So this is saying that some vi is not, so it's saying that there does not exist a1 up to, ak such that vi is equal to a1 v1 plus dot 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 plus ai minus 1 vi minus 1 plus ai plus 1 vi plus 1 plus 1 plus dot 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 plus ak vk. So what's it's saying is that I can't take one vector and express it as a sum of other vectors. Okay. That makes sense? Yes? We will now write down another useful equivalent definition. Can I erase what a vector is? What is a vector space? What is a vector space? That's the question. No. Well, maybe. Yeah, okay. Okay. No, it's a set. No, it's a set where you can add stuff and multiply it by a number. What is this word operation? That's such a long word. No, don't use long words. Only I get to use long words. Yes. The important part, like if you didn't write down the definition and instead you wrote down I can add stuff and multiply it by a number, that's better. That's better. It's more useful to be able to add stuff and multiply it by a number than be able to write down 8 axioms. Because at the end of the day, you have to add the vectors. Maybe. Sometimes you need to multiply them by a scalar. Okay. Right. So now, equivalent definition. Maybe I should keep writing in red then, because it's related. So equivalent definition. Of linear independence. So a1 v1 plus ak vk equals 0 if and only if I is 0 for all I. So some vectors v1 up to vk are linearly independent if the only way to add them up to get 0 is to set all their coefficients to 0. So just add 0 a bunch of times. Okay? Why is this equivalent to this? So proof. Let's prove it. It's a very simple proof. It will also probably be on the suggested exercises, but I will literally do it for you and then you do it again. Also a good way to learn, I guess. I don't know. I wouldn't know. Okay. So proof, let's go this direction, and then you can do the other direction yourself. That will be easy. So suppose we have vectors v1 up to vk, and if a1 plus v1, all of this is equal to 0, then it is necessarily true that ai equals to all the ai is equal to 0. So what do we want to show? We want to show that if this is true, then the vectors have to be linearly independent in that sense, right? So that no vectors in the span of all the other ones. Okay. Suppose this was false. Suppose this condition failed. So let's do by contradiction. Right? So let's show that if this is true, then it can't be not this. Right? Yes? People have seen contradiction? Yes? Okay. So suppose not linearly independent in previous sense. In the previous sense. Then, what can I do? I can take if it's not linearly independent in the previous sense, that means there is some vector which is a linear combination of all the other vectors, right? So okay, that means there exists an I such that Vi is equal to A1 V1 plus dot dot dot. Okay, I will introduce this notation. This notation means everything, like when I put a hat in a sum like this means everything except for the thing that has the hat in it. So it's like I omit this. Okay, everyone understands the notation? Good. Okay. So if this is true, then what can I do? Okay, and of course one of these has to be non-zero, right? Okay. In that case, what can I do? I can look at, well, 0 has to be equal to Vi minus all of these guys, minus A1 V1, minus A2 V2, plus dot, well, minus dot dot dot, minus AK VK. Okay, and there's some hat in here, doesn't matter. Okay. And okay, this has a non-zero coefficient in front of it, so this leads to a contradiction. Why does this lead to a contradiction? I showed that if it is not linearly independent in this sense, then it can't be linearly independent in this sense. Okay, so essentially, if one of my vectors is in the span of the other ones, right? So I can express one vector with the other one in terms of the other ones. Then if I just subtract the other ones from that vector, I get 0, right? But this guy said that, oh, I can only get 0 for my vectors if I add them up, if and only if, like, I'm just adding the 0 a bunch of times. Okay? People kind of familiar? Might be going fast, but that's the name of the game. Okay, so now I defined this whole span thing. I defined this whole linear independence thing. How is linear independence related to the span, other than just me using it to define it? Why is span so useful in this definition? Like, what's the point? What's the connection between linear independence and span? Go ahead.
Every single individual vector is not in the span of the others.
Okay, no, that's just the definition.
Oh.
I don't want the definition. I want, like, what's happening? What's going on? What's the point?
Well, they only care about the span of linearly independent vectors.
Why? Why?
Because for any non-linearly independent vector, you can just, like, substitute that with the linearly independent stuff.
Exactly. So when I was taught the linear algebra course, they made this analogy of workers. Suppose the prof made this following analogy. Suppose you have you're working in a factory, right? And you have, like, you're working in a factory, your mother's working in this factory, and you have some other third person working in this factory. So it's you, your mother, and some third guy, and then you guys are working in this factory. And it turns out that actually, one of the three, like your mother and this other person, they don't work that well. They're not good workers, so they're kind of redundant. But you can't remove both of them, right? Because then they still do a little bit, but they're really redundant. So you can remove either one of them and still have the same amount of work getting done. So okay, then the question is, do you remove your mother, or do you fire the other person in the factory? But okay, that's like in terms of linear algebra, right? It doesn't matter who you fire, right? Because the span changes, the amount of work still that gets done is still the same. But then I know other people have different opinions on firing their mother, so that's okay. So what's the point of this analogy? What did I just say? That's a great question. When I was taught this analogy was explained over the duration of like 10 minutes. It was more fun. There was like more story, more build up. I'm giving you the watered down version. So let's see. So what's the point? Suppose, and we'll kind of use this definition. Suppose I have some vectors, v1 up to vk, right? And suppose they are linearly dependent. So in this sense, this means that there is a vector which is in the span of all the other ones, right? Yes, makes sense? So in some sense, that vector is redundant. Do you agree? Because if I removed it from the list, so without loss of generality, let's say the first vector is in the span of the other ones. So without loss of generality is usually spelled WLOG, W-log, without loss of generality. Why is this without loss of generality? Because if, say, the third vector is the one that's dependent on all of them, just reorder them. Put the third vector in the first spot and then reorder them. Same thing. So suppose V1 is in the span of V2 up to Vk. What does this mean? This means that the span of V1 up to Vk has to be equal to the span of V2 ... Vk. Right? So I can take this, the first vector, the one that's redundant, remove it, and the span still stays the same. Why is it? Why is this the case? Well, what was the span? The span is all the vectors that I could possibly build out of V1, V2, V3, V4, Vk, right? If I can build V1 out of V2, V3, V4, Vk, right? Then surely, if I can build V1 out of it, then surely I can build anything that I use that uses V1 out of that, right? If I have the building blocks of V1, then I can build anything that involves V1 as well, right? If I can construct V1, then I can construct anything that also uses V1, right? Does this make sense? So the whole point of linear independence and span is vectors are linearly independent, means that you can't take out any more vectors keeping the same span. If you have vectors that are linearly dependent, that means you can take out some vector of my list and still have the span unchanged. So now we are essentially done proving the replacement theorem, or whatever you guys called it in 240, because it's obvious.
That was a quick proof.
It's well.
That is the replacement theorem.
Well,
Replacement theorem is given like a linearly independent.
Yeah, so I'm going to tell you.
It has to do with bases.
Oh, right. Well, it's like almost the theorem. I'll give you a lemma that lets you prove that theorem immediately. Well, not immediately, but well, it's obvious what a basis is. We'll get to that. So we'll talk about what a basis is in a second. Let's first talk about what we first need to know before we can talk about a basis. So we know what a linearly independent set is. Now let's talk about, okay, I still have some minutes. I'm planning to finish in maybe like 35 minutes. It's like today's long because I need to like cover all the relevant linear algebra again for the billionth time for some of you. That's okay. Hopefully you're having fun hearing the same thing over and over again. Okay, so that's good. So now theorem. Theorem is as follows. Given a linearly dependent, so given V1 up to Vk, let's take this a set. Linearly dependent, linearly dependent, then exists v I let's do v j1 vj, I know, some p, which is a subset of v1 up to vk, which is linearly independent. Good question. So let's first say what I mean in general, and then why I use this notation to mean it. So suppose I have some vectors which are linearly dependent, then I'm saying that I can take some of these vectors, and if I pick out some particular vectors out of these, then I can choose them to be linearly dependent. Oh, right, and the important condition. And span, that's the whole point, span of v1 up to vk is equal to span of vj1 up to vjp. Why am I using j? Because I want to use kind of the same, so j1, j2, j3 are indices from 1 to k, and it's just that I don't know which vectors I will keep, so I'm kind of trying, j1 is like some number from 1 to k. And I'm just like, I don't know which vectors I will pick, which vectors I will not pick, but I'm saying that if I have some finite set of linearly dependent vectors, then I can pick out some vectors and create some new set, which out of the old ones, and this new set will be linearly independent and still have the same span.
And say that P is less than
Oh no. But what if v1 is what if v1 is a linearly dependent vector? What if v1 is the vector that I will remove from my set, right?
You can do it without loss of terminology.
Okay, no, but that's like arguably more confusing, maybe.
Yeah.
Right. The point is that v1 might be removed or v2 might be removed. I don't know which vectors stay. I just know that I'll have some p vectors that will stay. And okay, maybe I can write like p is less than k. Okay, whatever. The point is I don't know the indices of the vectors that will stay in terms of the original indices, so I just give it like more indices. Yes.
I guess what do you lose by formulating it this way instead of how we typically do the replacement theorem?
Oh, I lose nothing, but I've now given you a almost fully rigorous proof of this in under 1 hour. Oh, yes. Okay, at least one vector is non-zero. Yes, at least one vector is non-zero. But I'm not going to write that, because why would you be playing around with vectors that are zero?
It does not hold. It's just does not hold.
Why would you be?
Actually, a set containing only one element is linearly independent by definition.
Okay.
So,
Also, a zero vector is not the zero. A zero vector is already not the zero vector. Sorry, it's not the empty set. If you have the zero vector, the span of that already has one element. Oh, okay. At least one of the vectors is non-zero. Okay, let's not. This is like, in some cases comments like this are useful and actually mean something. In cases like this, such comments mean nothing and are completely useless. But yes, so why is this proof obvious? Why is this proof obvious? Because I have finitely many vectors. They're linearly dependent. From this previous definition of linear dependence, this means, from this definition of linear dependence, this means that one of the vectors has to be in the span of the other ones. Meaning, I can remove it. Yes? And then the span stays the same. Like, literally by definition of what it means to be linearly dependent, I defined linear dependence in such a way that if I can remove a vector and the span is unchanged. Yes? By definition, literally. Okay, so if this set is linearly dependent, what I can do, so proof is Proof is very simple. I will not write out the full proof, but you will see what the proof is. The idea is remove redundant vectors until done. Until done. Okay, this is the entire proof. Like the replacement theorem that you learned in 240, if you spend a little bit more time thinking about it, you can prove the rest of the replacement theorem just kind of more or less from this statement alone. This is like what the replacement theorem is based on. And the replacement theorem, I feel like this is the more useful formulation. Like this lemma is more useful because you can prove like every theorem that you guys have learned, you can prove using like practically using this lemma. The fact that if you have some linearly dependent vectors, you can remove some of them, and then you will have linearly independent ones. Why? Because I defined linear independence in a way, meaning that if you're linearly independent, that means you can't remove a vector without changing the span, right? If you're linearly dependent, that means you can remove a vector and the span does not change. So what do you do if you're linearly dependent? Okay, you remove a vector, the span didn't change. Let's see, are you still linearly dependent? If you are, remove another vector. Keep doing that. You have finitely many vectors. You will eventually either get down to one vector, which will definitely be linearly independent, unless it's 0, but it's not 0 because stop. Or until you are linearly independent, right? So you either run out of vectors to remove, or you achieve linear independence and freedom. Yes?
Do infinite dimensional vector spaces exist in physics?
Yes, of course. That's what this is all about.
How?
Well, first we need to first we need to understand the finite dimensional case, and then we'll talk about infinite dimensional vector spaces. But that's for the quantum mechanics group. That's going to be day 2. In classical mechanics, we'll stick to more finite dimensional things for now. Okay. Do people understand how in this definition, from this definition of linear independence, it's completely the same as the usual definition of linear independence, and that you get this idea that if you have a linearly dependent set, you can remove vectors and then get a linearly independent set with the same span. Yes? It's kind of like if I have some building blocks, and I have some complicated structure made out of these building blocks. If I remove that structure, but I still have the building blocks, I can rebuild it again.
Django.
Sure, maybe. Okay, this makes sense, yes? So, definition. V is a finite dimensional vector space if let's write this in green maybe. Vector space if V is equal to the span, V is the span of finitely many vectors. Okay. Maybe let's do VP for now. VP. Span of finitely many vectors. These vectors need not be linearly independent, right? I can have, I can repeat the same vector 20 times and the span will still be the same. Okay, then we introduce the basis. So definition. Actually, maybe I should erase something and then write down what a basis is there. Yes. Is the span of any set of...
Just like if you take any span of a set, is it always a vector space?
Well, look, when you take a span, you need this multiplication operation to come from somewhere, right? So if I have an arbitrary set, and you also need the addition operation to come from somewhere. So if you just give me a set and tell me, give me the span of like these 3 elements in the set, okay, how do I add them and how do I multiply them?
After saying first that a subset of a
Well, it is a subset. So given a vector space and given some vectors, the span defines you some subset, right? Because, well, Here it is. It's a set. It's a subset.
Yeah, it is.
Okay,
And then
I can erase this. Yes,
It
yes.
is always a subspace, so I think, yeah, it should be.
Well, it's the smallest possible subspace. Okay,
Oh, yeah.
that was like first thing I said after explaining what a span is. Okay, good. Good. Okay, so linearly dependent vectors are vectors where someone can be fired or shot. Good. We're done there. So now let's talk about the basis. So, given a so definition. The finite the basis of a finite dimensional vector space V is a linearly independent set V1 up to Vn such that V is equal to the span of V1 up to Vn. Okay, so now we do our usual, let's stop and think. Colloquially, what is a basis of a vector space? What does it mean to be a basis?
part of the set which you call the vector space, such that you can use the operations which go along with the vector space.
Okay, that's a pretty good way to say it. I say it differently. I usually but that is actually good. I usually say like the basis of a finite dimensional vector space is V1 to Vn is a basis if I can take any vector and build it, any vector in the vector space, and build it out of V1 to Vn. And all of V1 to Vn are essential components. I can't remove any one of them because if I do, then I can't build all of the vectors. I can only build some of the vectors. Okay, that's what it is. Now, some important theorems. Let's see if I can prove them without thinking. So actually, let's do a definition first. Definition. So the dimension of V is equal to the length of the basis. Okay, now, important thing. The dimension of V is the length of the basis. Why is this not? Why is this a problematic definition? And why does it need a theorem or maybe a lemma? I don't know, or a proposition. Well, what's the problem with this? There's a problem with this. You answered too much. She also answered too much, but that's okay. Exactly. So the length of a basis, right? A basis is just some set of vectors which spans everything as linearly independent. There could easily be multiple sets of vectors that do this. In fact, V1 minus V2, V2 up to Vn is also a basis of this vector space, and it is a different one because V1 minus V2 is not equal to V1, right? And it also spans the whole vector space because I can still get V1 and everything in it. Okay, so I can have different bases for the same vector space. This is the key important idea of linear, like key idea that happens all the time in linear algebra is you can have multiple bases for the same vector space. And you want to, whatever you do, it's often useful to choose a basis and prove something with a basis. But then if you choose a basis in your proof, then you have to show that this choice doesn't matter for your proof. Okay, so proposition, this is well defined. This is well defined. Let's do we want to prove this, or is this like obvious? Maybe let's prove this. Okay.
What do you mean by being well-defined?
Has a unique
Like this well defined in the sense that this doesn't depend on which basis I choose. If I choose any any basis, it's always of length n.
Dimensions.
Yes, it is not. Proof. Let's see. Can I prove this? I don't know. Maybe I can't prove this. Okay. So suppose you have v1 up to vp and u1 up to uk bases. And what time is it? Oh, okay. I have to go faster. And p is not equal to k. Let's say p is less than k, strictly less than k, right? Yes. What does this mean? So let's see. This means that right. Very easy proof. Very easy proof. This means that so v1 is in your space, right? So v1. Oh wait, no. I wanted. Sorry. Which way do I want to go? I want to go the. Right. So I want. This means that v1 dot vp have to be in the span of. Sorry, I need to do this in the right order. Sorry, let me think about this. I want K to have extra stuff. So I want to show that everything can be, so essentially I want to say that U1 up to UP, all of these guys have to be in the span of V1 up to VP, right? So if I take the first P vectors here, that has to be in the span of these vectors here. And if U1 is in the span of V1 to VP, U2 up to UP is in the span of then this kind of uses the result. Sorry, I might be blanking. I'll think about this for one more minute, and if I can't do it, this will be an exercise. Let's see. It's supposed to be simple. If I take now I want to show that VI has to be in the span of U1 up to UP, right? So the goal is to show that VI has to be in the span of U1 up to UP from this. Okay, these are all of these vectors are linearly independent, right? So if I have U1 equals to that, U2 equals to that, U3 equals to that, so on and so forth. No, I can't. Right, so I want to do. These are some linearly independent vectors, and I want to essentially this would be proving like the next part of the replacement theorem, kind of, right? So, well, no, we didn't prove the full replacement theorem. This is kind of the next step to prove the full replacement theorem. The whole point is like to set it up. So I'm saying I have some vectors U1 up to UP, and they're in my vector space, so they have to be in the span of V1 up to VP, right? Because this is a basis, this is a basis. So if I take any vector here, it should be in the span of this. If I take any vector there, it should be in the span of that, right? So now I want to show U1 to UP. Now, okay, maybe let's do like this. Maybe let's do UP plus 1 is also in this span V1 up to VP, right? So there's one extra vector And I want to show that if I have some linearly independent vectors, if I add an extra vector, then this now has to be redundant. That's what I want to show. Sorry. They're linearly independent. Mm-hmm. Mm-hmm. Hmm. Okay. I will leave this as an exercise and give it because it's supposed to be a 4-line proof, but I am blanking and I didn't prepare. Sorry. I just need to save time. Otherwise, we'll be here for a long time. I can get lost on simple things easily. Like the whole point is like the version of the replacement theorem that you proved was very beefy and it was very confusing. Like the proof of that theorem to me was very confusing. I just want to be able to think in terms of like I have some vectors and I can just remove some of them and have that prove everything for me. But I'm blanking. But I feel like that's just for the purposes of what you guys were doing in that course, that made sense. For the purposes of learning all of linear algebra in one go, it doesn't make sense. Okay. So that's good. Right.
Can you conclude what the replacement theorem takeaway is?
I don't remember what the replacement theorem actually says. So the point is if you have a linearly dependent set, you can remove some vectors and get a linearly independent set. If you have a linearly independent set, then you can't add another vector and still have it be linearly independent. I guess that's the takeaway. I guess that's so. The first part was saying that if it's linearly dependent, you can remove to become linearly independent. And this says if it's linearly independent, then you can't add any more vectors to keep it linearly independent. Or actually, no. That's false. That's false. You can, yeah, if it spans the vector space and it's linearly independent, then you can't add more vectors to keep it linearly independent. Right? Like if you filled up the entire space and you're linearly independent, there's no more that you can add and still not stay in there. Okay. Sorry. Yes. Yes. Yeah, so this is kind of the idea here. Okay, now let's talk about, now, once again, quoting the professor who initially taught me linear algebra, I've done a crime to you, right? I've committed a crime. I've told you all of this about vector spaces. But, what was the study of linear algebra, right? It was about vector spaces and... No, I didn't say that word. Sure, and it's about vector spaces and how different vector spaces relate to each other, right? If I just have a vector space and it sits there and it does nothing, that's not interesting. Vector space should do something else should do something to other vector spaces. So that's right. So the idea of a linear map. So what's the point? So the point, I want to relate two vector spaces to each other somehow, right? And an obvious way to do that is with a map, right? So, everyone knows what I mean by map. Yes? Okay. So use a map. And if I want to relate two vector spaces, what's special about a vector space? What's special about a vector? Yes?
All the axioms.
No. The structure. So yes, but don't worry about axioms here. You should worry about the fact that I can take two vectors, add them, and maybe multiply it by a number. That's what's really important. And so that's the linear structure, right? The linear structure that can add stuff, multiply it by a number. So if I have some map, I wanted to preserve this structure. So we want to define a map that preserves this linear structure of a vector space. Okay. And so now we give a definition. Let V, U be vector spaces over the same field. Over F. So that's important. Over the same field. Either real or complex numbers. The other ones don't matter. And what do I want? What time is it? Good, 8:30. I should be able to finish in a bit. Right. So I want to define a map. So and then T is a map from U to V, from V to U. Okay. So what are the two things I can do in a vector space? Add two vectors and multiply by a scalar. So let's do the first thing. If I add two vectors, what should preserving the structure look like? Preserving, what's the structure? The structure is, if I have two vectors, I can add them. Preserving the structure in this sense means that if I had something that used to be a sum of two vectors before, then it should still be a sum of two vectors after I've mapped it. Yes? Intuitive? So this means T of A plus B should be T of A plus T of B, right? It used to be a sum of two things, it's still a sum of two things. Okay, so that's requirement 1 for being linear. Requirement 2 for being linear. T of lambda A, if something used to be a vector multiplied by a number, then once I map it, it should be some vector multiplied by the same number. Okay, intuitive. Of course, you can write this down as T lambda A plus B for all AB, whatever, and lambda, where A and B are in the vector space, lambda is in the field. Okay, but this is how this preserves linear structure. You know, things used to be a sum of two things. It still is a sum of two things. It used to be a number multiplied by a vector. It's still a number multiplied by a vector. In fact, the same number. Yes. Okay, this is what a linear map is. Now let's quickly understand everything there is to understand about linear maps between finite dimensional vector spaces, and we are done with the linear algebra review for classical mechanics. And then for quantum mechanics, we'll have to review 247 next time. Okay, I can erase this? Yes? Okay. Don't worry, it gets slower. It will get slower, a lot slower. Because I will, you know, I wouldn't then know what to say next, right? Because I'd forget. So I only really remember what I learned in my first semester of university. Mm-hmm. Oh no, but rank nullity. Now that you know that if you have some vectors and you can like remove them, that like gives you rank nullity if you really think about it. And so it's not that far from there. If we need it, I'll prove it, but I can give it as a suggested exercise. I feel like that'd be good. Yeah, that's good. I'll do that. But you know, you should be able to prove rank nullity on your own, right? I feel like that's a reasonable expectation for a first-year student who's finished the linear algebra course. Okay, so now the point. So now we do a calculation, which I think you have seen like at least 3 times now. Let's do it again. So let T from B to U be a linear map where V and U are finite dimensional. Now we do the amazing thing of let's fix a basis for V and U. Let V1 up to Vm be a basis for V. Let U1 up to Un. No, not F. I'm going to use the letter F. F1 up to Fn be a basis for U. Actually, I should have written this in another color. Let's use. Do I not have this? I'm poor. I need more colors. No, F. Good, okay. So now, what's the point? I want to figure out, so T is the linear map, right? It's a map. Usually if I give you an arbitrary map, how many values do I need to, what do I need to, so suppose I have a map, and I want to tell you what this map is. How do I do that? What do I need to tell you? Yes?
Where the basis factors go.
No, I said if I give you a map, any map. Right, so if I have some map, any map between any two sets, not a linear map, just a map between any two sets. How do I tell you what my map is? What do I need to do?
Mapping rule?
Yes, I need to tell you the rule for like every element. Where does that get mapped to? Every single element. That's a lot. That's a lot of work. I don't have time. I don't have all day. And so in many cases, that means I need to give you infinitely many specifications. Really bad. Turns out for a linear map between two finite dimensional vector spaces, you don't need to do that much work. In fact, even if just V is finite dimensional, you don't need to do that much work. Let's prove it. Let's proof by just computing it explicitly. So okay, T of V. So I want to see. Let's take any vector V, do T of V, and see see if I can somehow simplify that. Were you in my tutorial at some point, or no? Yeah. Oh, okay, that makes sense. Good. Okay. So we do T of. Since T is a vector in V, I can expand it in terms of the basis. Do you agree? AM, VM. Do you agree? Now what can I use? I can use the properties of linearity of this map. So this is equal to, let's write, continue here, to T. Wait, no. V1 VM. Put the T's in here, T's, and then I guess there's an A1 AM. Do you agree? Yes? Okay. Now let's look at this very hard and think about it. So, suppose I knew what TV1, whatever, up to TVM. This is fixed by the linear map. Yes? So if I give you a linear map, then you know what TV1 is up to TVM, right? But what are A1, A2, up to AM? Yes. What are A1, A2 up to AM? Yes.
Scalars in the theme.
They're scalars. No. But what do they determine? Kind of. Yes. Yes, but A1 and A1 up to AM determine what I input into the vector. Yes. If you give me a dial for each AI, that lets me control which vector I put in. Right? What we input in a map is something that I get to choose. Yes? TV1 up to TVM is determined by the map. So what I'm saying is, suppose I knew what TV1 is, TV2 is, TV3 up to TVM. I knew what the TV of the T of the basis is, right? Then, if I just knew that, then I can immediately figure out what T of any vector is, right? Because I know that T of any vector is just a linear combination of TV1 up to TVM. If I know what TV1 up to TVM is, given an input vector, right? I determine the input vector. If I determine what A and an AM are, if I know what TV1 up to TVM are, I can compute what A1, A2, and everything else is. Does that make sense? So, all of a sudden, before we had this problem of I need to specify what the map does at infinitely many points. No, I only need to tell you how the map acts on the basis. So this is like, I don't know, theorem, really important. To specify / define a linear map, you only need to explain how it acts on the basis. Right? So if you tell me how the linear map acts on the basis, you know how the linear map acts everywhere. Right? Because the basis, once again, because out of the basis you can construct the entire vector space. It's little building blocks. If you know where each little building block is sent, then you know what the final structure is on the outside, on the output. Okay. Yes, we agree. Now we do the final definition. Okay, so using this fact, let's try and if you have questions, you can catch me on the way to PhysU, which would also be closed.